Hello, this is Richard Mulholland, and today I'm going to show off my implementation of Tic Tac Toe with an AI using the General Problem Solver or GPS AI, symbolic AI. Now, all you have to do to get this project up and running is obviously install all of the dependencies, packages, everything like that. I think it's mostly just Pygame, but all of the requirements will be in requirements.txt, and the versions that I use will also be in there. I've only tested this on Python 3.12. You may be able to get this to work with another version. I just have not tested it out with another version, besides some really minor testing early on with 3.8, and that didn't work out super well, but you just have to change around a few things. It's not that bad. Anyway, once you get that all downloaded, you come here to Tic Tac Toe with GPS AI, open that up, press the play button, and here you are. You're met with a Tic Tac Toe board. Now, I would like to say one condition with this Tic Tac Toe game with AI is I was unfortunately, due to time constraints, only able to implement one algorithm for the AI, which is actually just the algorithm of being greedy. So all it will really do is try and find the shortest path to victory for itself. Once it finds the shortest path, it will just go along that path. It won't purposefully obstruct you, though sometimes it will obstruct you, just by virtue of trying to win. But yeah, so it's not super clever, but it is an AI. Now, it's tic-tac-toe, so all you have to do is click and you can place the first cell. I'm going to go for the middle here. Oh, look, it chose to do that. So we can see already the only path to victory with that being included would be the top row. So it's likely going for the top row. So I can mess with it. I'm actually not going to mess with it. So you see, it's going for the top row again. I can pretty much tell that it's going to go for this one right here. So I'm going to go for that. Okay, now it sees that the only path to victory for itself would be this bottom row. So that's what's going for right now. Obviously, I can win by doing that or that. I'm just going to mess with it. See? So now it knows, hey, I can't win because I placed the X there. It knows that the AI can't win. And so it just chose a random spot between the two. In the end, I won. You can actually reset the board with R so you can play another game. I'm going to give it a little bit nice of a thing here. I'm going to go up here. Okay, so it went for the middle now. Which makes sense. That'd probably be the most probable location for it to go. I'm going to go with that. So we can see again, it's probably going to try and do that. Yeah, so see, sometimes it can win. It doesn't even always come down to you just, being stupid or, yeah, just purposely letting it win. Sometimes it will win on its own. It's just not very clever. Let's play one more game here. I'm playing games instead of turning in my assignment. Okay. Okay. So we see it's going to move there. So I'm going to block it. And we can see that the only possible path for it to win is right there. So I'm going to obstruct it. And then, see, it didn't purposefully obstruct me there. So I can win. Now, that's the last game we're going to play fully, but technically, I guess we could play this one fully. Since you are the first player and the AI is the second player, if you just full on race it, you're always going to win. So you see it's going for this top row here again. I'm going for this bottom row. Since I'm the first player, I'll always win because it's not going to purposely obstruct me. I just wanted to put that in there just to let you know. Okay, now that I'm done with that, I'm going to go over to the implementation. If you don't care to see that, you just want to look at the code itself, it's pretty beautiful in and of itself. But yeah, thank you. Okay, now for the second part. I'm just going to go over the implementation, kind of what I did, maybe some choices and why I made those choices, kind of give a brief overview of everything. So first, we're going to go over tic-tac-toe with gpsai.py. That would be this file right here. So this file is kind of the one that, again, you play to play the game against the AI. This brings everything together. You can see right here we're importing the game from tictactoe.game. We're importing the GPS player from GPS and everything like that, right? So it's just basically bringing everything together. This running the game loop, everything like that. Pretty self-explanatory. And then I have two main folders right here. So we have GPS, or the General Problem Solver, that's the AI right there. And then we have Tic Tac Toe, which is the game itself. So let's go into Tic Tac Toe first, just because I think it's a little bit easier to explain. So this board is just a class, that's all it is. And it basically just makes the board itself. So we have get corners, update, and render. So update just looks at all the cells, makes sure that everything is good, and basically says if there's a winner. Right? It checks for a win condition. Render just draws it. Um, yeah, and it also draws the I guess win state. So we saw both players win actually. So we saw X and O win. It will show X wins and O wins. It will draw that as well. Cell.py over here, that's responsible for each of the 9 cells themselves. Interestingly enough, we will see this later on in game.py, but you can actually change the amount of, like the width and the height of the tic-tac-toe board. It doesn't work with the AI, unfortunately, just because you have to implement a 5x5 AI. And I've only implemented the 3x3 AI, but you could play it on its own as a 5x5 board. I have done it. So this one, you have update state, right? So yeah, basically, uh, once you click on a cell, you want to make sure that it's either X or O. So that's what update state does. And then render obviously just draws it. So we see if it's an X, we draw an X. And if it's an O, then we draw an O. Alrighty, and then these are just enums. So these are the colors that I used. If you really want to, you could change the colors here. And the states are just the states. So state empty is 0, state x1, state O is 2. It just makes it a little bit nicer, syntactic sugar as some people like to call it. And then here's game.py. So this actually makes the game itself. This is where Pygame is based as well. So here we actually have board size. So if you change this to like a 5, for example, it will create a 5x5 board. Again, it won't work with the AI because yeah, again, the AI is only implemented for a 3x3 because it's a symbolic AI, but you could technically do that. You can also make it bigger if you'd like. Note that it's always going to be a square, so if you change this to a 5, it will be a 5x5. If you change this to like 2 million, it's going to be a 2 million by 2 million pixel screen. So here's the game itself. Pretty cool. So we have process input here. This sees if you're clicking anywhere. That's what's down right here. And if you want to reset the game. We have update here. This updates each of the cells, and it also sees if the game is over. You can see it right here and right here. And then render is just basically calling everything else out, right? Like rendering the board itself, which then renders all of the cells. And it also makes sure to reset, like wipe the screen every time so it's not overlaying over itself. Which actually wouldn't be that bad for tic-tac-toe, if I'm being entirely honest. So, but yeah, and then we have process GPS input here, and that just takes in a cell and processes the GPS input. So this is when you're using the AI. If you're not using this, then it would just be player like person player versus person player. Or if you want to play with it like by yourself, go ahead. And then we have the game loop function here, which just runs process input, update, and render, just the normal game loop itself. Down here we have a thing that I used while testing it. I don't think you can use it anymore, unfortunately, because the inputs are a little bit messed up. Alright, now moving on to the actual AI part, which I'm sure uh, Professor, my professor would appreciate a little bit more. So here's my implementation of GPS. Originally, I was trying to just go straight forward with a completely general GPS implementation and hopefully get that to work with Tic Tac Toe. I found that I could do it to them for the most part. It just didn't end up working in the end. There were some things that I just had to change because they just did not work with Tic Tac Toe the way that I wanted them to. So unfortunately, this is not a pure GPS implementation, but it is pretty close. So obviously we have the init function, but this first one, find all step paths, basically takes the goal, finds um, finds all of the steps needed to reach the goal, or all of the step paths to get that goal. We'll see later on what that kind of entails. And then it finds all of the steps that are needed in that step path there. And that's kind of what this is for. This is actually a recursive function. Kind of fun to use recursion in an assignment, in a project even. But this one basically just calls itself over and over, finds the step path, and then if it's not possible to do, or sorry, if all of the precons are already met, like if all of the preconditions are already met, then it's just going to return the step path. And if it's impossible to meet them, then it's going to return an empty list, which up here just won't get added because we say if step path, right? And this evaluates to false in Python, an empty list. And then, again, it calls itself over and over and gets the step path there. And then print step path. I don't actually use this one, but you could. It just prints the step path that you're currently using. And then precons for step. This just gets the preconditions for the step that you're currently on. And then get current step name. This just gets the name of the step that you want to do next, or that you're on right now. And then increment step. That just so it actually deletes the step right there. So it deletes I guess the next step, the current step in the step path, which makes it so you move on to the next step. And you can see right here, if there's not a possible step path, it will just return true, and that will make the GPS name down here, the GPS player, the AI player. It will make it just choose a random. So. Alrighty, now to move on to step. This is kind of just a data structure implemented as a class. So it just stores a name, preconditions, add list, delete list. Basically what you would expect from a GPS step. Now here's another enums file. We just have uh, each of these. I've never actually ended up using those, but names to tiles, that's what I ended up using because this is how we say, hey, if the AI wants to move in the top left, then we want to change the 0th cell to be an L, right? So that's what we use that for. Then here's the actual steps that I use to implement them. So you can see, I mean, Tic Tac Toe is a simple enough game that we're not deleting anything. So, or at least my implementation of it didn't delete anything. So that's all empty. But yeah, JSON, super nice, way easy to read, uh, at least in my personal opinion. So yeah. This one was just for testing out. It will basically just load in the 3x3 steps, and yeah, you can test it out a little bit yourself. And then here's the AI player itself. So this actually implements the same exact logic as the get 3x3 plans right here. So it gets the 3x3 steps from the 3x3 steps JSON, and then reads them in, and it creates a GPS for itself to use, and then it will check if the step paths are still valid. I just put this everywhere because we need to make sure that we're constantly checking if it's valid. Right, so here we have get current step name. Again, that's similar to the one in gps.py, where it's just giving you the name. That's so that we can use it with the enum here to actually move, to actually represent a move for the AI. And then we say if there's no step paths, then we're just going to choose a random one. And then if there are step paths, then we're just going to get the current step name from the GPS. So we're going to get the next step or the current step. Now we have increment step here. Again, it's pretty similar to the other one. So we see actually if the GPS does increment the step. If it doesn't for whatever reason, then we want to choose a different step path. That would likely be because it's not a valid step path, which we've already checked for, but it's just a nice redundancy there. And then we just set it to 0. And then here we have choose step path. Again, we have strategy here. It wouldn't be that hard to implement a different strategy because this is the strategy right here. That's it. And so it wouldn't be too hard to implement a different strategy. I think you are kind of limited just due to the implementation as well as the AI model itself. But you could implement another one pretty easily. So we kind of just find the best length and the best step path and then use that. When we check step paths valid, this one is pretty self-explanatory. We're just seeing if each of the step paths in the GPS all step paths are valid, and if they're not, then we want to take them out of all step paths, right? Because we don't want the AI trying to play a cell that I've already played, right? Or the player has already played. So yeah, that's the basic overview of the implementation itself. And yeah, thank you for joining me along on this ride, and I hope you have a wonderful day.